tell you all I know about him. So he used to be at Philips and led a team on speech recognition, and that team, as far as I remember, had the best real-time speech recognizer at the time. And I don't know what the time is, but I know that his demonstration was in Berlin.
Well, 93.
In 1993. And it was real-time and everybody was admiring. And then he left Philips and is at the University of Aachen, where he leads again a group and has many famous students, some of which are written down there as co-authors. We also know that each team here has at least one nice student in it, some of them more. And they made enormous progress in machine translation. I also know about him that he likes to eat well, and his wife is a doctor.
Right.
Hermann now.
Okay, thank you very much for the introduction. So the title...
Oh, I should have said that he was at 2 workshops here.
Right, I was here in 95 and at one of the first workshops that took place in Cape, in New Jersey.
Right, good.
Rutgers. Okay, so this is, as Fred said, joint work with some of my PhD students. Let me start with an overview. So what is the formulation of statistical machine translation? We're going to look into more details for the alignment models, lexicon models. We're going to have a look at the generation problem. We're going to discuss some experimental results. And what I would like to do at the end of my talk is to revisit the base decision rule and raise some questions or point out some problems. So I think most of the people here, or half of the people here, I guess, in the audience work on statistical machine translation. So they know the basic formulation. We are given a sequence of source words, F like French, and we want to translate them into a sequence of target words, E like English, and of course the sentences can have different lengths. So J is the position for the words in the source sentence, and I the position in the target sentence. And the base decision rule tells us, okay, or no, we cannot do perfectly well. So we say, okay, we want to minimize. We want to at least we want to minimize the number of decision errors. And then the statistical decision theory tells us we have to look at this posterior probability and maximize it over the possible target word sequences. And then we can rewrite this posterior probability as a joint probability. And then we have 2 independent probability distributions. The language model, which is supposed to take care of the syntactic semantic structure of the target sentence, and the translation model itself. Now, of course, you might ask why doesn't this look identical to this one? Well, yes, but on the other hand, here now we have 2 probability distributions that are really independent, and the idea is, okay, they will help each other to find the right decision, hopefully. And we can do the modeling process independently for each of the 2. And then we have the generation problem or search problem. We have to carry out the optimization explicitly. So the resulting architecture looks very much to the architecture we have in speech recognition. We have a sequence of input symbols, that's a sequence of source words. We want to generate the target words. We have to look at this joint probability. We have probability distributions. Now this one is this will be modeled just as a trigram. Of course, you can try to do context-free grammars also. So people here at the workshop understand I'm trying to do this. Here, this is too complicated to be used directly by using a table. So it's too complicated, so it will be decomposed into a lexicon model and an alignment model. And this is an example taken from the Canadian Hansards. So here we have the sentence in English: what is the anticipated cost of administering and collecting fees under the new proposal? In French, that's en vertu de lait. So there's been some pre-processing, some transformation here. So sometimes we do some transformation steps and pre-processing steps and maybe some post-processing steps in order to make the task simpler for our algorithms. So en vertu des nouvelles propositions, quel est le coût prévu d'administration? So d'administration was turned into de administration, so it better fits the English words of and administering. D'administration et de perception, D3, again D, originally was de les. Okay. So the notation I'm going to use E for the target words, I are the positions, capital I the length of the target sentence, F for the source words, J the position for the source words, and capital J the length of the source string. And in the beginning we will start with alignments. Alignments are the mapping from J to I. So the whole alignment will be denoted by A1 to capital J. So this is one possible alignment, and it looks very much like a state sequence in from speech recognition using hidden Markov models, and there will be a strict analogy. So the states can be identified, well, the positions here I should say can be identified with the states of a hidden Markov model. And when we do, let's say, phonetic-based hidden Markov models, each state has a phonetic label, state label, and these state labels are actually the words. And we are going to have a translation lexicon. This translation lexicon is the exact equivalent of a emission probability distribution, a discrete emission probability distribution.
George wants to ask you.
Yes?
Just go to your mic. We can't hear well from here.
Aha. So I have to speak up.
No, the mic is only for the
It's only for the recording. Sorry. So, but maybe here are the seats. Please come down. No. Why not? Is that a problem?
Some of us do lip reading, so maybe you should face us.
Okay. Okay. So I will try to do that. Okay. So maybe I can to know what I'm talking about. I need my slides. Okay. So yes. So we will start with defining alignments in such a way that they are mappings from the source positions J to target positions I. And the presentation I will give will be different from what you find in the famous paper by the IBM group from '93. There was a paper where they introduced a sequence of translation models that are called IBM 1. Well, it was called their model 1 to 5, but now typically they are called IBM 1 to IBM 5. And the results of what they did is more or less identical to what I'm going to present, but the way I'm going to derive the results will be different. So don't be surprised when you have a look at the paper and you do not see a one-to-one correspondence. What I will do is I will try to do a derivation which is more directly linked to what we know from hidden Markov models in speech recognition. And strangely enough, I don't know why, I never found this direct analogy to the HMM models in their papers. I don't know why, but they did not do this direct analogy. But we will see there is a direct analogy. So first thing we do is we introduce a length model. Typically in speech recognition that is not done. That is well somehow swept under the carpet, or we say we're going to have a sentence end symbol, but we do not seem to care much. I mean, in practice, even here in translation, it does not matter much, but it's, let's say, for the sake of completeness, I'm using it, and it was also used in the original presentation, the original paper by the IBM group. So we have a length model and a probability distribution that is then conditioned not only on the hypothesized target string, but also the length of the source string. So the observations are the symbols of the source string, and then the alignments are introduced as a hidden variable. And often this length model, or typically, if at all, if we use it at all, it's simplified in such a way that we say, okay, the dependence is only on the length of the hypothesized target string and not on the individual words. And then this is really factorized, this probability distribution is really factorized like the corresponding distribution in hidden Markov models for speech recognition, discrete hidden Markov models. We make it dependent, we make this, we have a product over conditional probabilities, and each conditional probability depends on the full history, and then we simplify it by saying, okay, there is a emission probability distribution that depends only on the state that we reach. The state that we reach is a word in the position A sub j. And here we have a transition probability or alignment probability as it's called here. And here we still retain the dependence on all predecessor positions. And we will specify this probability distribution in more detail. So we have the lexical model. So this is the resulting model. We have the lexical model, as I said before. This is just a big table, in principle. And now we do one of these choices. Either we do HMM model, that means the first order model. We say, okay, of all this history, we are only interested in the immediate predecessor position. And we retain the dependence on the length of the hypothesized target string, because we know this must be a normalized distribution over the positions I. And the other thing which was done, or which is equivalent to what is called IBM2 model in this paper of 93, is we say, okay, here we have all predecessor positions. We do not really look at the predecessor positions, but we know we are talking about the J's position. So we assume there is an explicit dependence on the index J of the position. And then you are getting this distribution. And this is what is called nowadays IBM2 model. And the consequence then is that because it's the first order model, we can carry out this summation here explicitly. This was shown by in this paper by IBM in 93. And then what we get is this identity. So we have a product over the positions J, and then a sum of J as remember J as a position in the source sentence. So we have a product over these positions J and the sum over these positions. So what we basically do is we say this word, the probability of seeing this word, is modeled as a mixture distribution where we have a sum over all the contributions from each position here. Now, of course, we could have derived this simpler by just saying, well, we are having such a decomposition, such a model, and then now we have interaction of this word in position J with each position I in this string, and this is exactly this decomposition. By the way, I always, my convention is to use PR for a more or less unconstrained probability model, or the true model, or the true distribution, true but unknown distribution, and lowercase p is a specific model that we are using, model assumption. Okay, so this really just could be derived directly by making a mixture, using a mixture distribution. Now, when you look at our public papers and also the software, GISA++, that gives implementation of all these training procedures, I think we were not always careful in terminology. Typically, when we in our papers talk about IBM2 and Hidden Markov models, we do not use exactly these models. We go one step further and say we reduce the number of free parameters, because basically here you need a three-dimensional table. Well, you have the conditioning on these two conditioning events and this predicted event, and here it's even a four-dimensional table. And that was done in the original paper by IBM. When we do it, we typically go one step further and say, okay, we want to reduce the number of free parameters, and how can we do this? Now suppose we have this sentence, ja, ich denke, wenn wir das hinkriegen an beiden Tagen 8 Uhr, an example from the Workmobile task, well, I think if we can make it at 8 on both days, typically you find that word, the best alignments, the correct alignments you want to have tend to lie around the diagonal line. So we can say we want to measure the distance from the diagonal line. This is what we then call homogeneous version of the IBM2 model. Or when you use first order model, you can say, okay, this position, the choice for this position, probability, should depend only on the distance to the predecessor position. So we are talking about relative positions, relative distances. And this will be is then called homogeneous variant of the Hidden Markov model. So often in our papers, when we just say IBM2 or Hidden Markov model, we really mean we are using these homogeneous variants. So you just have a table for all relative distances, and then you say, okay, in order to make it a true distribution, I have to do this renormalization. And similarly, in the case of first order models, you measure the distance, position distance in terms of positions to the position of the predecessor grid point, and then you do this again, the same type of renormalization. And I mean, the problem with original models is that absolute positions, they are not really meaningful from a linguistic point of view. Absolute position does not say very much. And there is one small problem, but it doesn't seem to be a problem in practice. These formulations, these models do not fit directly into the EM training. This renormalization does not allow us, I think, if I understand it correctly, to do the EM algorithm exactly. But without that, we can do, of course, it's well known, we can to train these things. This is the usual EM algorithm, or forward-backward algorithm, as we know it from speech recognition, and this is even much simpler because it's only a first order, zero order model. Okay, now what we really want to do is generate the target stream. In order to do that, it's better to have a direct dependence on the position I of the target word. So that direct dependence, I mean that we invert the modeling. So we say we are going to look at, we invert the alignments. So we are going to look at alignments that are mapping from the positions of the target words, positions I, to the source words. Because in the end we want to generate the target sentence step by step. And of course, so we are looking now at subsets here because there might be a mapping, as you see here in this example. When we try to invert this mapping, we have to cover, we go from here to here, we need 3 positions. So we are talking about sets, subsets of the source axis positions. And of course, there is a constraint that we would like to, coverage constraint that we would like to hit each position only once, each source position. So we introduce now these inverted alignments as, again, as hidden variables over which we have to sum out. We factorize them. So we say, okay, we are selecting, now the product is over I, which is not the variable here we want to predict, which is not the index of the string we want to predict, but the conditioning string, which looks, maybe it looks strange, but in the end I think when you give the right interpretation to these probability distributions, it should be, I think it's correct. So we say we are talking about the possible positions and the words in these positions. And we condition it on all the predecessor positions. And then again we factorize this by making assumptions that this, the words, or first we specify the positions bi, let's say. And they depend on the word we are hypothesizing in position I, and because we have this coverage constraint, they should depend on all predecessor positions. So the constraint is when these two are not, if there's an overlap between the two sets, then the probability should be 0. So we do not allow any overlap. And we have so we have specified the positions, and then for these positions, we have to specify the words in these positions depending on the hypothesized target word E in position I. I is the index here. And now you can go one step further by saying, okay, this is decomposed into a product of independent distributions. And then we have a lexicon model, which is which represents a word-by-word correspondence, and that's exactly the same as we had before here in these models. Maybe we use a different type of indexing the table, but basically the table as such is the same, or can be the same. Okay, now of course this is still complicated because here we're talking about sets of position and not a single position. So you have to decompose this further. And then you will arrive at these models, IBM 3, 4, and 5, and there are complications that might occur. So the simple case is that you say, okay, I have selected a position here, and now I'm going to select another position, and then I'm going to make this probability depending on the distance. So we're again talking about relative positions, but now relative positions along this axis. Before we had relative positions along this axis. What might happen is that we also allow the empty set. That means this word here in this position I-1 does not have any direct corresponding word along this axis. This is called referred to as a word with fertility 0. Fertility is defined as the length, as a cardinality of this set. And the probability distribution over the fertilities, that depends on the words that we are hypothesizing in position I. So you have to include in your equations, in order to make it complete, you have to include this special case that you might skip a word, or a word fertility 0. Now you might have, as I said, these are really in principle, these can be sets. So you have to worry about cases like this, where you have to place several words in the same line, and how you're going to define the probability distribution. Well, you say it's again to be a first order model left to right. As soon as I have selected the first position, the next position I make depending just on the distance here. So you have a left to right model for positions in the same line. And also you might have cases like this, where you have selected 2 positions in the preceding line, and you're going to select a position in the next line. Then will this be dependent on this last one, left to right, or maybe on this one, or maybe on the average of the 2? And actually in IBM 4 and 5, they define this to be the average. So in that sense, it's not strictly a first order model anymore. And when you want to do search, exactly that produces some complications. In practice, I think it does not really matter. You could as well say, I'm going to have also a first order model for this type of dependence. This would actually simplify some of the equations. Well, at least a little bit. Okay, so we introduce fertility. We have to include the case that the fertility is 0. For fertility larger than 1, we have to decompose this, and we do it in a left to right way. And again, more or less first order. Not exactly, but in most cases it's a first order model. And we are talking about relative positions. And there's always this coverage constraint that, at least ideally, we do not want to allow to select a position that has been selected before. Okay, I think that's all I wanted to say about this. Yes, the next thing then is search. Of course, we want to use this in search. I think I have to watch my time. We're going to use a trigram language model. We are going to use these inverted alignments. So what we're really interested in is to find a mapping from the target positions I, and for each target position we're going to specify the word, the target word in this position, and the source positions that are covered by this word. And then when we put in everything, we just have the model as before. There was a product over I, if you remember. Okay, but now we can include the language model here into this product. And for completeness, I have included the length model, which again, as I said before, is not very important. So 3 decisions to be taken: length of the target sentence, the target words themselves, and the positions that we cover along the source axis. And there are conflicting requirements. On the one hand, we would like to cover all the words along this source axis, and in order to be able to apply the trigram, we want to do the evaluation or the forming of hypothesis along this axis. And covering all these positions, for people from computer science, they know this is equivalent in some sense to the traveling salesman problem. And here it's known that we can reduce the complexity a little bit by using dynamic programming. It's still exponential. You can do other things like beam search and A star, as we will see. But in addition to that, we do not really want to allow all possible reorderings. I think nobody has really done that, and it never paid off to do that because you introduce too much freedom for the algorithms. So typically we use either what is referred to as IBM constraints, or special constraints that we develop when we are talking about when we're doing translation from German to English, and also the other way around.
Hermann,
yeah?
Would you explain that picture once more? Just a picture.
Just a picture?
Yes.
Well, in a simple case, let's simplify things. If we're talking about a situation where we only fertility 1, what we want to do is we want to build a hypothesis from along this axis. So we're looking at this.
Which is the English axis.
Which is the target axis, yes.
Oh, okay.
So we want to place a word here, and we have to select a position. Suppose we hypothesize this position, J. And then we have to ask, how can we get there? And we have to look at these possible predecessor positions. Assuming, okay, we do not have fertility 0, and and that we do not allow that the same position is covered twice. In order to satisfy the coverage constraints, we really have to check what are the positions covered before. So when we go back here, this pass is not allowed to hit this position again, because that would violate the coverage constraint. And what we do then in practice is we include a vector, a bit vector, that keeps track of the positions that have been covered. So this is the picture to explain what we are doing. We have different probability distributions and there might be conflicts, and so this whole search criterion is used to find the best compromise between to explain the data that we see. And okay, I think this is for people from speech recognition, this is well known. So the dynamic programming for the traveling salesman problem, how can we understand it? Suppose we have 6 cities and we have distances. We want to find a round-trip tour in such a way that each city is visited exactly once. Now what we do is we redraw this network in such a way that the coverage constraints are incorporated into the graph. So we have a new graph, a super graph, that expresses these coverage constraints explicitly. So let's, for example, select this node here, 5. This 5 occurs several times here, but in this case, here the incoming arcs are all arcs that cover the same source position. So we have this one, this is 2, 3, 4, this one is 3, 2, and 4, and this one is 2, 3, and 4, and so here we assume the starting point is 1, the starting city is 1. So here, these 3 paths are equivalent in the sense that they cover the same cities. So from the dynamic programming point of view, we can take a decision here about the best incoming edge. So we can apply dynamic programming directly to this supergraph by going from left to right. And this is really the spirit of the algorithm by Held and Card, which was, I think, developed in 61 or 62 for the traveling salesman problem. So these nodes here that we are using, this new graph, each node represents a subset. And in the algorithm, this subset is denoted by capital C, and we have to do a dynamic programming recursion over these quantities, these auxiliary quantities. So C's are the cities that were covered, J is the cities that we just have reached, and D is the accumulated cost for visiting all these cities. And we're basically doing the subsets are constructed by increasing the cardinality of these subsets. So we start with subset of cardinality 1, then cardinality 2, and so on. Now we do the same for translation. So for simplicity, assume one target word corresponds to one source word, so we have fertility 1. So we use basically the same arguments, the covered positions and the last position, the subset and the last position, and we have to include, because we're going to apply a trigram language model, the dependence on the words that we have selected, the hypothesized word and the predecessor word. Now for the general case, we have to introduce a fertility. So when hypothesizing E, we know there might be different fertilities because there is a distribution over the fertilities. So we have some maximum fertility, and we have to introduce an additional index as a running fertility and to include recursions over this fertility. So that's a little bit awkward, but it can be done. It's after you have defined the problem in such a way, it's quite, let's say, mechanic to do all the steps. Okay, but as I said before, nobody really does it, as far as I know, without any constraints. So we include some reordering constraints, and there was one type of constraint that was suggested by the IBM group in their, I think, in the patent on search. So it's nothing to do with the IBM models. It's a different thing. It's not related to the models 1 to 5. And the idea is to say, okay, basically I move from left to right, but I'm allowed to select the next position as one of the next 4 positions, if I did not skip any position so far. If I skipped one position, then I have to select as next position either this position or one of the 3 next positions. If I skipped 2, it must be one of these 2 or the next 2. And if I've skipped already 3, it must be the next one or one of these 3. So we have the impression that these reordering constraints are well suited for French to English and English to French, where we have different positions for the adjective and the noun. In some cases we found that for German-English translation, both directions, this is not very very good, and sometimes it's not sufficient. So we introduced some other types of reordering for this language pair. So the problem is in German, in this case, my colleague cannot visit you on the 4th of May. So cannot visit is a verb group, but in the German sentence, this is distributed over the whole sentence. Kann, the auxiliary verb, and then not visit is at the end. I mean, not exactly because we include punctuation marks here, but it's basically the end of the sentence. And these are cases that cannot be handled by these IBM constraints. So this is a special type of constraint we use. Christoph Tillmann has, I think he has given a talk here where he has worked out all the details. So still, even with these reordering constraints, a full evaluation of the dynamic programming tables or hypothesis is prohibitive. So we do some heuristic search or focused search. Well, first of all, a simple thing to do is what we call observation pruning, as in computing mixtures in speech recognition. We limit the number of candidates that we evaluate. So this is nothing to do, let's say, with the search as such. It's just we evaluate the, we're looking only at the limited number of possible translations for the word F that we observed using a unigram language model. Typically this number is 12 or even smaller. Then we have the choice between either A star or stack decoding using priority queue or beam search. Basically in both cases we are still doing dynamic programming evaluation. You should always do this recombination, but you have a different strategy on the order in which you fill this table. And in beam search, this is very similar to what we do in speech recognition. We do it in more or less in a position synchronous way. Now exactly position synchronous is not possible because we have to allow at least some reordering also here. So it's not exactly synchronous, but it's virtually position synchronous. And there are two types of pruning. Coverage pruning, where hypotheses with the same set of covered positions compete against each other. And then we have another type of pruning where the set does not have to be the same, but the cardinality. And okay, again, I think we have had a number of papers about these things, and experimental observation is that beam search in this case is much more efficient than A star. And right now, given the models we have, maybe poor models that we have right now, search does not seem so much of a problem. Okay, also we learned from speech recognition that we can use these techniques to generate a word graph. So instead of taking a hard decision here, just remembering the maximum, we remember all the other promising candidates, and in such a way we can construct a word graph. And I think there are groups here that are using the word graph, so people are familiar with that. So let's move to the experimental results. Most of the things we did were done in the context of speech translation. So when we started, it was 96. All methods were originally developed for speech translation. So you have the speech signal, you do recognition, and then you have a non-perfect recognition result, and then you use this recognition result to do translation. And but fortunately, as it turned out, nearly all methods, actually, as far as I know, carried over to written language translation and also to large vocabulary translation. Because in the beginning it was not clear, we were not going to have as many training data as IBM had for the Canadian Hansites. So it was not clear whether we could do with the limited amount of training data that we had. That was one big question mark. And the other thing was, okay, we know speech, it's not perfect, so the input will never be perfect. Can we handle that? So one project was a German Verbobil project, limited domain, language pair German-English in both directions. Then at about the same time we had a project Eutrans, which was in some sense more exploratory. The target was, let's say, just to study these techniques. So the group in Valencia, Enrique Vidal and Pablo Casacuberta, they were also involved. They were looking at statistical approaches, but also at finite state transducer approaches. And here we actually had the task for translation of speech and text, but this was much smaller than this huge German project. And right now we're having a couple of other European projects, C-Star, where it's still limited domain speech-to-speech translation. We have a PF-Star project where we think we compare different approaches to speech translation. And we also have one project on translation of written language or text, but here there's some emphasis on interactive translation. Actually, I think there are, when I look around, I see two representatives here of the groups involved. Okay, so Raleigh is involved from Montreal and also Xerox from Grenoble. So the results I'm going to present will be mainly for Wordmobile. So this is a database. We have for Wordmobile about 60,000 sentence pairs, 500,000 running words, vocabulary 5 to 8,000. The number of singletons was something like 40 words. And in addition to that, we used a what we call manual lexicon, that means conventional dictionary, with about 12,000 entry pairs. And we did some very simple pre-processing steps. It's a limited task, so it makes sense to do some categorization for the persons, for the cities, to try to normalize numbers, times and dates, spelling, and we did some splitting of German compound words. Now, so far, what I said is based on a lexicon that is a single word to single word lexicon, a statistical lexicon. And it turned out that it's much better. It results in significant improvements using word groups in various ways. So how can we find these word groups? We symmetrize the training by swapping the roles of source and target language. Then, with the best models that we have, we compute the best path, or Viterbi path if you like, and then we form the union of the two directions, source to target and target to source. And then we get an alignment matrix like this. And then we extract all blocks that are possible. So here you do not see all possible blocks, but some examples. So here, this could be a possible block. We could not extract this one. 3 by 3 would not be possible, because then we would not cover this one. So this is not possible. When we want to include this one, we have to do this whole block. So all these possible blocks are extracted up to a length of 7. But right now I have heard that Franz Hoch went to a length of 8. It's a recent evaluation. Okay, and we basically remember all of them. We extract them and we remember them. And, okay, before coming to the details, let's summarize how we do the training. So we have several models, IBM 1. IBM 1 I did not explain. IBM 1 is a simplified, a particular case of IBM 2, where we assume that the alignment probabilities are uniform over all positions of the target samples. Maybe that's not an interesting model, but the interesting thing about it is, from the mathematical point of view, it's a single optimum that the maximum likelihood function has. So it's good to start with that model and use the result of this model to initialize the other models, because you do not have to worry about local optima. So we have, typically in training, we use a sequence of models of increasing complexity. We start with these IBM 1 and 2 mixture models, and then switch to HMM, and go on with the fertility-based models, IBM 4 and 5. And as I said before, we do symmetrized training. And then, at the end, there are several ways of construct your models. Either you can say, okay, I'm going to use only, let's stop here. When you stop here, you can say, I'm going to use the original IBM approach, using model IBM 4 or 5. Or you can say, I want to include phrases or word groups. In order to do that, you should symmetrize your training procedure, and then you have to define in which way am I going to use these results, this alignment matrix. You could, for example, you can compute relative frequencies for these word groups. Or you can do what we call alignment templates, which goes a little bit beyond these relative frequencies, and that was mainly done by Franz Hoch, and I think you know these details, so I will skip them and just present the result. So this training procedure is available in Software Gisa++. So here we have a comparison for these different approaches: single words, phrases, where we basically use relative frequencies, and these alignment templates that include some additional generalization capabilities. And so there are 3 systems. We have different reordering constraints: monotone, strictly monotone, which is clearly not sufficient. We have German-English, so the translation was from German to English. This type of constraints that are based on looking at on interpreting the reordering that is needed for the German verb group. And now, of course, talking about evaluation, we have to talk about the evaluation measures. Now, when we started in 96 or so, these were the two measures we typically use. First of all, we said there might be several reference translations, and we are going to select the best one for each source sentence. We use word error rate, as we do in speech recognition. You might say this is a silly thing to do because you have the problem with the word order. Okay, but nevertheless, it's easy to apply and straightforward. And the other extreme case is that we do not care about word order at all. This is what we call PER, position independent word error rate. And then about 2 years ago, IBM and later NIST came up with this accuracy measure based on using n-gram precision and some gravity penalty, and depending on what type of averaging you do, geometric mean or arithmetic mean, you get different measures. In addition to that, we also did some subjective evaluation, we call subjective sentence error rate. And this was all these things were done mainly for verbmobile. Verbmobile is a limited task, so that means it was easier than, let's say, for this TIDES task, Chinese, English, Arabic English, I guess. So it was easier for the verbmobile task to make sure that these subjective measurements were consistent, transitive, and reproducible in some sense. So we had a data bank where people could look up what they had done, what their measurements, what their judgments had been before. So I think we were able to reach some level of consistency and reproducibility. Higher, I would say, than in the case of these TIDES evaluations. So here are the results. PRE is accuracy measure, so in order to compare it with error rate, in order to make thinking easier, I converted it to an error measure, 1 minus PRE. So we see there's an improvement when we allow word reordering in this German-English style. When we move to phrases, there is an improvement. So for subjective evaluation, it's about 10%, absolute. When we allow the reordering here for the phrases, we get another improvement. Actually, this one is the phrases are a little bit more complicated than I said, because when you do phrases, you actually do some segmentation. And I think we tried to carry out the sum over different summations using some word graphs. So Richard Senz did the work, he probably is in a better position than I am to give the details. So I think there was a sum over the possible segmentations, assuming a uniform probability distribution over the possible segmentations. And the graph was constructed, word graph constructed for both cases. Monotonic constraints, no reordering, and German-English reordering. And again, there is an improvement. But still, when we use the alignment templates, there is some more improvement, small one, but we found this is consistently true that these alignment templates give the best performance on all tasks. So here's the difference in subjective evaluation is only small, 1.4, but nevertheless. And you see all these measures seem to be consistent. There's always, if we have an improvement here, we have an improvement here, here, and here. So I think the details of these measurements do not matter that much at the present level of performance. It's just that you should be able to compare different algorithms and draw a conclusion which one is better. So these word groups, in particular alignment templates, allow significant consistent improvements. We found this, we did most of this work in verbmobile, but it was also found to be true in other tasks, large vocabulary, written language, large vocabulary translation. My interpretation is that we are using a context-dependent lexicon rather than a context-independent lexicon. Of course, it's only context within such a phrase that we cover. So we do not cover context between phrases, but we are able to cover context within these phrases. And that really seems to help to improve translation quality. And, but what I'm not sure, I mean, when you do this segmentation to phrases, you have to worry about the segmentation, you do the probability distribution. So I'm still wondering whether it would be possible to do a direct factorization into position conditional probabilities. But so far I think we were not able to achieve that goal. And of course, what is important here is the normalization effect. You basically remember all word pairs, word group pairs, phrase pairs that you saw in training. which is a concept of a whole approach in translation, namely translation memories. And here they are found automatically. So I think that's an interesting thing. So memorizing everything that you saw in training is good, but of course the critical thing is how good are you in generalizing to events that you did not see exactly in the same form in training. So that's, I think, still an open question. I think we never did it, so maybe we should go back and analyze our results and see whether we are able to get also improvement in cases where we did not see the corresponding word pairs, word triples, word n-crams, whatever it was, in our training data. So that might be an interesting exercise to analyze our translation result under that view, from that point of view. So the next thing is what is the effect of morphosyntax. Now, of course, English is not a language where morphosyntax or morphology is important. German is not really a highly inflecting language, but it's much more inflecting than English. So this work was done for translating from German to English. Again, it was a verbmobile task. We used a commercial tool that is available from a Finnish company. What was it? What is it? Linksoft, which I think was brought up by Microsoft. Yes. I think they were, at least 1 or 2 years ago, they were brought up. Anyway, we used this software and we did some pre-processing, annotation, whatever, on the incoming German source sentence. And we did two things: reordering. So we changed the word order in the source language to better match the word order in the target language. And this was applied to, in particular, to question version and separated German verb prefixes. Also, we could apply it to German compound words and multi-word phrases, but I think in the verbmobile were basically these two things. And then the other thing is really to do morphological analysis, to improve lexical coverage and do disambiguation. Let me give an example. So, the German sentence, wollen Sie Plätze reservieren? English, do you want to reserve seats? So we have here, wollen Sie, we do some morphosyntactic preprocessing, then we know this is the auxiliary verb, and we do this inversion, and then we do the translation. So this is done automatically, and then we do again a transformation to construct this word order in English. Another example for the German verb prefixes, the word to leave in German is abfahren, but when you use it as a finite verb form, it is wann fährt der Zug ab. So fährt and up is a separated verb prefix. So what we do is we do morphosyntactic analysis here. We find out, okay, these two words go together, so it should be abfährt. So we apply this preprocessing to the whole corpus. Then we do the translation, and on this preprocessed sentence. I don't know why I put in here. So when does the train leave is the correct translation. I don't know why I put in here exactly. So I guess this is an example really taken from the
Hermann,
database. Yeah?
why don't you transform directly wollen Sie reservieren Plätze? You know, why don't you, I mean, that would be English, you know, and in the sense that you gave, which had the last verb really at the end, it would have fit quite well into the English.
I cannot give you a direct answer to your question. You would have to ask Sonja Nies who did this work. But maybe here we do not have, we need additional words. This wollen Sie has to be do you want. So there's one word more. I'm not sure.
Yeah, but it is do you want to reserve. So wollen Sie reservieren.
Yeah, but it is this wollen Sie. It's not just want you, it's do you want. So I think it does not really handle this very well, the original models. Mm. It's not only, I mean, what you say is maybe would even more be true for the case if you could say in English, want you. But this is not orthodox English, you have to say, do you want? And these are three words that have to be combined with these two words.
Well, I'm not talking about the fact that you can't affect the square, you know what I mean, yeah. But the sequence, sort of where the English would be, okay, well, I'm sure you have your reasons, but... Okay.
So let's look at some other examples referring to concerning the lexicon. I will explain what we do later on. Just let's start with example. For example, you might have the sentence mit dem Zug ist es bequemer. In English, a translation by train, it is more convenient. But this is a comparative of convenient, of the German equivalent of convenient, bequem. and it was not seen in training data. So it does not know what to do with it. So the baseline system, the alignment template system, translate by trainities, and it says it's unknown word, and just puts in the German original word. By doing morphologic analysis, it recognizes this is a comparative form of bequem Merl. It knows the base form, or the lemma is bequem, so it puts in the English equivalent of the base form, which is not exactly correct, but it's much better than just saying by trainities something, and here it says by trainities convenient. It's not exactly the correct meaning, but it's close to the correct meaning. Other example for disambiguation is, here German is ambiguous. Zimmer means room or room, so it can be singular and plural. And when you use the baseline system, it's not able to distinguish. But by using additional parts of speech information, what it does, it produces, we have two rooms. Other example, ich würde das Stadtteil vorschlagen, denn es ist das billigste. So das in German can be that, it can also be the, just the article. And also then is a little bit ambiguous. So it's also able to get these words right by using what we call hierarchical lexicon. And so the problem is that we have a limited amount of training data. They are unseen. Well, we use only full forms for the words. We don't do any analysis. So there are many unseen forms. There are low frequency words and ambiguous words. Like Zimmer, as I said, in German can be singular and plural. So what we do is we use a hierarchical lemma text representation, and we combine these representations using a maximum entropy model for the lexicon. So what do we do? For example, the German word comes. We apply this morphosyntactic or morphologic preprocessing, and then the system knows, okay, this is a verb, indicative, present tense, singular, second person. So this is a full form. So we remove the information about the person. This is a second level, and so on. So we have a hierarchy of levels, and then the last level is just the base form, or lemma, or base form, whatever you want to call it, or the next one is here verb indicative. So we have this, we define this level of hierarchies, and they are combined using maximum entropy. And here are the experiments we performed. Again, translation from German to English. Language model was based on the full part of the corpus, I mean the English part of the corpus, and it was tested on 500 sentences. Error rates are given using this additional morphosyntactic analysis, reordering hierarchical lexicon. Baseline system are the alignment templates, and here we varied the amount of training data to see the effect of this preprocessing. Of course, when you have huge amounts of training data, we expect the effect will be small, but when the amount of training data goes down, we expect the effect should be larger. And this is actually what we see. Here we went to the extreme case that we did not use any training data for the translation model. Of course, we used the monolingual corpus to train the target language model, but I think this is a monolingual corpus, this is always easy to collect. And here we used the conventional dictionary with about 12,000 entries, I think. So here the full training baseline system. So reordering buys us something, again, for all three types of errors. And again, some improvement by using the hierarchical lexicon. Baseline for the 5K case is a little bit worse, but the improvement by using these morphosyntactic preprocessing steps is larger in total. So we go down here from 34.1 to 31.9, 38 to 33.9, and also here in the subjective error rate. And even more when you do not have any training data for the language, for the translation, for the lexicon. So the observation here is experimental observation. There's a small but consistent improvement using this morphosyntactic analysis, and the improvement is larger when the amount of training data gets small. So that's basically all I wanted to say about the experimental results. So let's revisit Bayes' decision rule. Of course, well, the starting point or the justification for the Bayes' decision rule is to introduce a posterior risk, which is the expected value of expectation value, we're calling it expected value of a loss function, and you sum over all possible strings in your target language, both over strings of different lengths and When you have the length, you still have to fill in the words, and in principle you have to go over all possibilities, and then you get the posterior risk for the observed source string, and for this hypothesized target string. And of course you want to select the target string that minimizes this posterior risk, and typically, without going into details, what people do is they always use this 0-1 loss function, which basically reflects the sentence errors. So we say the error, this loss is 0 only when we have the correct length, when the two strings have the same length, and when the words in each position are identical. So tilde is the quantity over which we sum out, and without tilde, E and I are the decisions we hypothesize. Okay, and then when we use this loss function, this is what we get. But as we know from our discussions about MT evaluation, we do not really look at sentence error, we're looking more at the words. So for the word errors, the correct loss function is the Levenshtein distance, but this is difficult to handle analytically, and as far as I know, there is no closed form solution. I know there are people here, there was also one project here a couple of years ago about this topic where people try to do a star in order to carry out the sum, if I remember correctly. What I'm trying to do is here to try a more analytical approach where you try to really consider some cases where you can derive a closed form solution or virtual closed form solution for the decision rule. So what you can do first is we can assume that we have the same length, and then maybe I should have to use a table, blackboard. So we can assume the same length, and then we really have to go along the diagonal line. So we have here tilde and here's the other string. Now, of course, we might have word reordering, so we do not have to stay around the diagonal line, but we can allow deviations from the diagonal, maybe limited ones or maybe unlimited ones. So we are then somewhere here when we say, okay, we have to find the best matching word. We might also introduce weights where we say, okay, well, first of all, I have to change the, well, in order to make this meaningful, I should have changed the length, sorry. Okay. So we also allow changes in the length. But somebody could say, we would like to go somewhere along the diagonal line to account only for small changes in word order. And we can also say we could introduce weights to penalize deviations from the diagonal line. And in this case still, I think this is not well defined from the mathematical point of view, because you would get the minimum when you just say, okay, I'm not going to select any word. So capital I without tilde should be 0. So you have to introduce an error count for the non-aligned words. And this is something we could try. And I mean, originally I tried to work out these things for speech recognition. So maybe have to redo the mathematics to check whether everything is okay. We just transferred the results, carried over the results from speech to translation. So this is then what we get. We make additional assumptions that we have different words in our hypothesized target string. Then I think we can carry out the sums over the probability distribution. And this is what we get. We have a probability distribution about the possible length of the target string. This is an absolute deviation between the hypothesized target string and all possible lengths. And here we have the decisions about the words. And this is what I call word posterior probability. So we hypothesize a length I, we are given the source sentence, we ask what is the probability of seeing word E in position I, given the total, or hypothesizing the total length capital I. And this can be computed, suppose we have a generative model, as we have with all these models, IBM 1 to 5 and hidden Markov models. We can compute this probability as a marginal probability where we sum out over all possible word sequences, but we fix the word in position I. And then by renormalizing this, we are getting this posterior probability. And of course, what we still have to do is to do the maximization, the minimization of the cost. And assuming, making some simplifications, what we get, I think, under certain conditions, is something like this. That means we are looking at position. Suppose we can guess the length. then we have to look at this quantity. And this is similar to a quantity that we use in speech recognition, and we used it as confidence measure in speech recognition. And we are also using it as a confidence measure for translation. Nicola Oeffing here, he has done some work along these lines, and of course you have to be careful in evaluating this one. It's computationally complex. You have to use forward-backward algorithm on word graphs, on best lists in order to really carry out the sum. But I think it's interesting because there's a chance to get really closer to the real base posterior risk. I think we do not really understand is the effect of the length model and what is the relation to the aberration scores that are used in MT right now. So it will be interesting to see then, whether in 6 weeks we will have more results about this. The other question is, the other thing is base rule for speech translation. As I said, most of our work, at least in the beginning, was done on speech translation. So we actually have 3 levels. We have the speech signal in the source language, we have this symbol string in the source language, and we have the target string. And typically here, we just use a speech recognizer and then use the output. You can try to using the best and best list or word graph to account for word errors. And the question is how to handle recognition errors. Just to be more specific, we tried to do the things in previous projects, and we never were able to get real improvements over using just single best output. So this still is an open issue, whether we will be able, when doing translation, to recover from recognition errors. So in order to do that, again, we have to reconsider the base decision rule. So we are given the speech signal in the source language. We want to hypothesize target string. So we can rewrite a probability like this. So the source string does not show up here. The source string is really a hidden variable. This can be factorized like this without any assumptions. Now here we can make assumption which I think is very reasonable. Here we assume we are given the sequence, the source symbols in the sequence of symbols in the source language and the sequence of symbols in the target language. And we have to generate the speech signal in the source language. But for that task, the symbols in the target language are not really needed or do not contribute much. So without, I think it's it's a very weak assumption to assume that this dependence is not needed, and this is then what we get. So this is a typical acoustic model. And here we have a sum over all possible source strings. Often what we do instead of the sum, as usual, or as we often do, we use the maximum approximation, and this is what we get. So now the result is, in order to do the recognition, we really should use the joint language model of source strings and target strings. And as I said before, we looked at this, but we were never really able to get improvements over just using the single best output of a conventional recognizer, so there was no effect of the target language model here. So maybe as I said at the beginning, there will be I think I had it in the view graph, I did not mention it. We will have a new project, TC Star, which is unlimited speech-to-speech translation. And I hope we will have a chance in that project to look at this problem in more detail and hopefully to make some progress. Okay, so I think I can skip this one. Let me summarize. The analysis of many translation experiments in Verbmobile, Oiltrans, also in TIDES and other projects has shown, well, first of all, that for spoken language, the statistical approach seems to be more robust than rule-based conventional approaches, in particular when you have ill-formed sentences, speech recognition errors, or long sentences. Now for written language, it's also competitive with classical rule-based methods, and again, at the workshop yesterday and the day before, they really said, okay, the output, even using human judgments, the output of the best statistical system nowadays looks better than the commercial systems. When we really did this exercise and were looking at the outputs, I was horrified. I was shocked by seeing what what the systems produce, but this is what they found. Okay. So there are a couple of open issues. I think we always have a lack of syntactic structure in the sentences. Nearly always, we have a lack of syntax. So maybe really grammar-based language models could make a difference. And I still tend to think this situation could be different from the situation in speech recognition. In speech recognition, it's more of a sequential problem. We have to, the sequence of words is monotone with the acoustic signal, and it's that problem we face. But here we really have to generate the target sentence, and the word order is more free, and so I think a grammar-based language model could make a difference. Well, we can do it without looking at the word alignment, but ultimately I tend to think that it should be better to link these grammar to what we do in the word alignments. I think right now the training that I presented is just based on a context-independent lexicon, just a single word to single word lexicon, and I think it should be possible to get improvements by introducing context dependency into the training explicitly. Morphosyntax again is not integrated into the training and alignment modeling. It was done as a post or pre-processing steps. So we did the alignments and we kept the alignments fixed. Then we did all these analysis and then we retrained just the lexicon. But we did not the whole training. We did not do the whole training. Decision rule that I just presented, maybe it's possible to get a closer link to the MT evaluation measures. And also, when we really do speech input, maybe it's better to achieve a better coupling between recognition and translation. And that's the end. Yes?
Yeah, I have a question about homogeneous HMN the homogeneous variant of HMN. And you mentioned that there is a small problem in the EM training. Can you tell us a little bit about that?
Well, I mean, in order to do the EM training, you have to write down the Q function, and you have to take the derivative. And typically in all the models that we know that you find in the literature, there's a closed form solution when you take the derivative, and that's the reason why you do the EM, because it's so nice. But when you do this renormalization, then you do not arrive at a closed form solution in the, what is called estimation step. But in practice, we do not seem to have the impression that it is a problem. I mean, always back in speech recognition, 10 years, well, maybe 15 years ago, we did these things already. We did not care very much about the approximation. We did not think it causes problems, and the same seems to be true here.
So this is just a mathematical problem, and the practical problem.
Yeah, but also I think the alignments here in speech recognition are not very important. The alignments, when you do not have your lexicon, the alignments are important to find the lexicon one. But as soon as you have the lexicon, the alignment probabilities as such do not contribute very much to the overall performance. Again, similar to HMM in speech recognition, the transition probabilities there are typically not very important. They are maybe important in order to find the right emission probability. But as soon as you have the emission probabilities, the alignment probabilities, well, they still help a little bit, but they are not very essential. Also, what I did not say, now yesterday I learned at the meeting that both IBM and CMU, they do just IBM 1 to initialize the training, and then they do just the HMM in both directions. And I'm not sure whether they do the homogeneous variant or not, but in some cases I know they do even only Viterbi training. Also in our experiments, I think we had some improvements when we went up to IBM 5, but when we just used HMM, the difference was not that big.
Yeah, model 4 is typically a little bit better than HMM.
Yeah.
But not much.
And it's much, I mean, the HMM has the advantage that you can do EM algorithm, that you have a sort of closed form solution to carry out the sum, I mean the EM algorithm. But for IBM 3, 4, and 5, there's no closed form solution anymore, and you have to do approximations to the sum. So HMM is much easier to implement. Yes?
So you kind of did in your experience pruning beats A star. And there are a couple of things that you might mean by that. one is the number of hypotheses that are followed, and the other is the amount of time spent per hypothesis. If you prune, you don't have to store it on a queue to call back later. Is that what's making the difference, or is it the number of hypotheses?
Well, in summary, it's both. It's the number of hypotheses, and it's also the absolute time, and also the absolute amount of memory. And we also, for A star, we derived what you need upper or lower bounds, at least we did it in the right direction, I hope. And we derived really exact bounds in order to estimate the cost or probability of the remaining path. And that was incorporated, it was really A star in that sense. I mean, there was
yes, although, how confident are you that the heuristic you have is...
No, okay, I did not go into the details. By the way, Nicola Höfing and Franz Ocht did this work, and it's still going on, and you can talk to Nicola, she's here. She knows maybe the details better than I do. Let's look, I was not very exact in the specification. So, I think for A star there was no heuristic apart from the fact that we did this observation pruning and nothing else. Well, we had a memory constraint. We could not go beyond, I don't know, 2 gigabytes or so. Is that right? Okay. And so here we really, and this here we give up the guarantee of finding the optimum. But in practice, this was always much faster, did not require so much memory and so on. But maybe Nicola can give more details.
Actually, it didn't have a great effect on the translation quality, as long as you don't do too much, because the reasonable beam size can be much more efficient, but still get the same translation quality. So basically,
but I think it's the same experience as a speech recognition, because when you do beam search, the advantage is that you do not have any normalization, not any is maybe saying too much, but nearly no normalization problems, because you compare hypotheses competing against each other that cover the same input data. And that's a very big advantage. And here, of course, you have to account for when you do this one here, you do not have exactly the same positions, but you have to try to account for the difference in these positions, and you can use the same estimate as for A star, and that's what we do. Any other questions? Comments? Yes?
So you talked about these two constraints on in the search, in terms of the IBM constraints and the German English. What about actually changing the model?
What about what?
It's difficult. That's
changing the model rather than
to what?
To something that more accurately reflects the kind of behavior you want in the translation. So the point of alignment is to explain actually two sentences that are generated by humans, whereas we don't really want our translation systems to add in that much complexity. So I think typically, so for instance, in the current implementation of alignment templates at ISI, use a much simpler movement model, because the power of the model that IBM came up with it's far too powerful for what you can actually produce.
What do you mean much simpler?
It's just a penalty for how far you realign the templates. So we're not using the distortion models from the original IBM work.
But I think when you just do monotone, but again, that does not buy you much. If you just do monotone alignment, it's a monotone alignment at the level of these word phrases, then you do not lose much.
The gain by reordering is quite small, so that's basically the same line that is alignment probabilities are not very powerful, at least as they are situated right now. So either more than 4 probabilities, which are then very sophisticated three-dimensional.
I mean, the thing is, we're talking about alignment probabilities within a phrase or alignment probability between the phrases. You're talking between phrases, okay.
I was just curious as to what you...
Well, yes, but I think in the end, I tend to think that, if you really want to model these alignments better, you have to include the target language model, the grammatic structure of the target language model. Which I admit that's probably difficult to do, but in the long run, I think that's maybe the way to go. But I admit but here some people are working on it, so maybe We just have to wait. And then the problem will be solved in 6 weeks.
Or proven impossible.
4
That's
weeks
even
now.
even more difficult. To prove that something does not work is even more difficult. Yes.
Yeah, I have two simple questions about the morphological back-off model. The first is, maybe I'm just not understanding, when you say that you back off, you say, okay, I'm not going to look at the person, I'm just going to look at the number, tense, and mood of the verb.
Or including.
Does that mean that you just include all translations of things that that mood would? Or I had this weird idea that you're translating a word without a person, or something like that. That's probably
That's
not
cool
right.
here. So really the lexicon is, we're still having the lexicon, what is it, P of F given E, and then we have an exponent, sum over these features M, HM, and they depend on F, E, and all, what we're talking about the source sentence, about this one. All these things that are written down here, verb, indicative, all these things are put in here as additional argument.
Right.
And this is renormalized over, what is it, F, and this is the function that we are, the approach we are using. So here, in each function, we know the target word, full form, we know the full form of the source word, one of these levels, and also the lemma of it.
And would you expect that, you said it helps more when you have less training data. Do you also expect it to help more when you're translating outside of the domain that you trained in?
Maybe not this version that we have, but ultimately in the long run, I think that should be possible to do, yes. But not maybe with the present version that has too many limitations that we have right now. But in the long run, I think it's a way to go. So I tend to think what has been done in conventional, linguistic conventional approaches is not that much wrong. What they do not have is, they do not have a consistent training procedure. They do not put probabilities on all possibilities that they have, or not in a consistent way. What they do not have is a consistent criterion for generating the target sentence. So they are, it's my impression, they are at a loss when they are conflicting requirements from their models, and they do not know what to do. And that's really the advantage of this statistical approach, that you have a consistent scoring criteria. So maybe one interesting experiment would be, but maybe that's impossible, but in theory I think it still would be interesting to have a conventional system, to talk to the people that understand this conventional system, and try to put probability on all the things that are in it, maybe just rough estimates. And then have a consistent generation method that generates the target sentence. Consistent that really tries to maximize the probability that you're using in our approach. So I tend to think even when the probability estimates are very crude, still this consistent criterion for generating the target sentence should help a lot. But that's a speculation a bit.
Yeah, for the morphosyntax, I was wondering whether instead of having large versus small corpora, perhaps you keep the corpus size the same and compare, let's say, Chinese English versus Czech English.
Yeah, but Chinese says nothing about morphology.
So that's why I'm thinking that
Chinese says nothing about morphology.
That's why I'm saying that it might be more of a, it might be a better comparison, because there you really don't expect to benefit from this model at all, whereas in Czech you would. If the corpora were the same, it would show a big difference in performance.
So you are saying for Czechs the difference should be larger?
Yes, yes.
Okay,
So
okay.
I'm
Or Arabic maybe, but then you need
Arabic,
but
yeah.
okay, but in order to do that, first you need a good morphosyntactic analysis. I don't know whether it's available for Czech.
It is.
For Czech, yeah, that's why I thought about Czech.
And the corpus is also, bilingual corpus also available. So maybe. But also ultimately, as I said, I think morphosyntax, well, it should go hand in hand with the alignment model, and the alignment and training procedure. So here this was still a sort of post or pre-processing, and ideally it should be part of the whole model, which is not the case yet. Any other questions or comments?
Well, thank you, Hermann.